Hello everyone, George here, and we are once again working with OpenCV, and in this video we are going to specifically be talking about erosion, one of the morphological operators that we can use inside of OpenCV. Now many times we'll want to separate regions of an image. This is typically performed through masks, which are binary black and white images. The mask informs which regions we are interested in, which is usually white, versus those we are not interested in, which are black. However, getting a mask from images can be very tricky. Using various methods can result in masks that are noisy, that don't cover everything we want, or sometimes they're even broken up into multiple smaller pieces. To fix these problems, we have a few morphological operations we can perform. Two of the simplest are erosion and dilation, and specifically we're going to be looking at erosion in this video. As their names kind of indicate, erosion is about removing elements, and dilation is usually about expanding or growing them. Each of them use what's referred to as a kernel or structuring element to decide how to manipulate each pixel of an image based on its surrounding neighbors. We can call white pixels the foreground and black pixels the background. What happens next is that when we have this kernel or structure element, we're going to move that structure element to every single foreground location of our image. In our case, every white pixel that we have. And we center that structuring element based on wherever we decide the origin to be on that structuring element. As the structure element is moved around from foreground location to foreground location, we say whether it fits or hits the image. Fitting is where the image and structure element agree on their foreground values. Hitting is where there is only partial agreement. That means not every single foreground element is going to match up. Two of the simplest ways to modify a mask are through erosion and dilation. The difference between them is that erosion requires all foreground elements to agree, while dilation only needs at least one. So with our first example, why don't we start with one of the most easy ways of eroding an image away, that is with an ellipse and a 3x3 structuring element. To make this work, we're going to need to include some elements inside of our project, and in addition to that, we're going to need to make sure that we have some library files added that we didn't have in our prior project setup if you were watching any of the earlier videos. So first, let's do some includes. We'll do #include OpenCV2 /core.hpp for all the core functionality. Then let's do #include OpenCV2 HiGUI so that we can actually display everything. Now we'll do #include and we'll do image OpenCV2 /imageproc. And the last thing I'm going to do is include Ctype H, and that's just because I like working with C types because they define very rigidly exactly the size. Finally, let's add in some using namespaces to make our life a little bit easier. We're going to be using the standard namespace and as well as the CV namespace. All right, so we're going to do a couple different examples. So why don't we go ahead and create a few functions to encapsulate each of these examples. So first of all, let's just do void example1. So the first thing we're going to do is go ahead and create our structure elements. So let's go ahead and define a mat object. We're going to call this our image that we're going to be operating on. We're going to call getStructuring element. And the first thing we pass in is what kind of structuring element we want to use to create this. We're going to use morph_ellipse. So it'll create an ellipse based upon the size that we define. So our size is going to be a rectangle, basically, and our ellipse is going to fit within the bounds of that rectangle. So let's do size, and let's do something, let's say 20 by 20, something a little large. I want my object to have values within a range of 0 to 255, so I'm going to multiply that by 255. Now I'm going to do Kernel is going to be equal to getStructuring element. I'm going to do morph. And for this one, I'm going to do a cross. And let's do a size. And typically your kernels are much smaller than your actual image, although it doesn't have to be. And we're also going to multiply this by 255, just so that we have values that range between 0 and 255, 0 being black and 255 being white. And let's do another kernel. So let's do kernel full is going to be equal to getStructuring element. And in this one, I'm just going to do morph _rectangle, and I'm going to make the size of this, let's just say this is also 3 by 3, and I want to multiply those elements by 255 as well. All right, so now we've got an image in two different kernels. To actually produce an eroded image, all we've got to do is type erode. We first pass in the image that we're going to be operating on, which is just image, and then we pass in our output. For our output, we need a mat. Let's do output. Output. Now we specify our structure element, which for right now, let's just do the first one, which is kernel, which is our cross. And then there are additional fields that we can enter in. And these matter only if you're going to be changing where the anchor is for the image. For us, we're using a 3x3 object. The anchor is going to be by default in the center, which we're going to use just fine. If you wanted to change the anchor to one of the corners or a different location, you would then put in those coordinates here. You can also change things such as the border type. You change the border type because as the kernel is moving around, how do you deal with the corners and the edges? Because technically your kernel might slide off into a completely missing part of the image. The border expands the size of your image so that as it moves around, it always has some pixel as part of the structure element. And you can choose whether or not you want the border to be a specific color, if you want it to repeat whatever the pixel was next to it, and so forth and so on. So with that, we have now an eroded element. Let's now create our named windows. So named window, and then we're going to do our name, which should be original. And then we're going to have this as window underscore, and we'll do, might as well just do free ratio. We'll do the same thing a second time, changing the name from original now to eroded. Now let's go ahead and IMShow. We're going to do that for both of these. So the first one's going to be original, and then we're going to show the original image we created. And the second one is going to be eroded. And that is going to be our output. All right, now let's do a wait key 0 so that we actually can see the results. And we need to call our function example1 inside of our main loop. There we are. And let's go ahead and hit run. All right, so here are the output for our two different images. So here's the original one right here, where you can see we have our ellipse, which takes up the entirety of the image. And then we have next to it a slightly reduced in sized version. Now remember, we're using the cross as we're moving throughout this entire thing. Let's actually look and see what that looks like. So let's go over here and do another IMShow, and we'll do kernel. And we'll call this one just kernel is what our output will be. And let's make that a named window as well so we can modify its size. So let's do kernel. There we are. Let's stop this and hit run again so we get that image out. So here we go. This is the kernel that's iterating over our entire image. Remember, it's very small. It's only a 3x3 element kernel, and it's going throughout this original image, and it's finding whether or not all of the foreground pixels, which are the white elements, agree. So here it's moving along, and you'll notice that here's the first foreground pixel it finds, so it moves to there, and then it looks to see whether or not this set of foreground images match what we have here. Well, at this location, the center's good. The center points are both foreground. However, to the left and to the right, which are both foreground images here, they are background. Therefore, this pixel is going to get rejected and turned to a value of 0, which you see over here. Now we come to the next line and we move over and over and over, and we come to this point, and then we look above, to the left and to the right, and we see whether or not it works. And as you'll notice, it does not work above and to the left. Therefore, this is rejected. And in fact, this entire line is going to end up rejected until we get to this point right here, where the top, bottom, center, left, and right all agree with what we have here, in which case that pixel stays along for the ride. Then we move on to the next row, and what happens here? Well, we continue to evaluate it, and at the very edge, it's not going to work. That gets rejected. But then here, you'll note that we have the top, left, center, bottom, and right element, so that pixel sticks around right here. Now, what if we did something a little bit different? What if instead of using a cross, we used that rectangular version instead? What we're going to notice is that's far more restrictive. That is, it requires that not only the cross shape be included, but also all of the corner values as well. Therefore, when we get to a point like this one up here, that's rejected. But then when we get down here, which was previously accepted, this pixel right here, you're going to notice that it does get rejected as well because it does not have these two side points, these two corners as part of it. So let's go ahead and see that in action. So coming down over here, we have kernel full. We're going to copy that, and we're going to use that as our output right there. And instead, for our erosion of using our cross kernel, we're going to use our full kernel instead. Let's go ahead and hit run now and see what happens. So here's our original image. Here's our kernel, which of course is completely white. It's a 3x3 white element. And if you come over here, check it out. Look, we lost that top portion, and we've actually eroded in further on the various sides as well. So now let's do another example that kind of shows how erosion is going to work, not just on these simple created structure elements that we have here, but instead on maybe some more complicated images. So what I've done is, inside of Photoshop, I went ahead and created a template for us to work with. So here's the template that I created. Relatively simple. It's a series of black and white pixels where we have regions that are pretty much solid, that have different structures to them, such as a cross and so forth, and some broken in parts. We also have, of course, this checkerboard area, and I actually blew them up to be larger than just 1 pixel for each element so that we could see what these different kernels will do to each of them. So go ahead and save out an image like this if you want to create one yourself, or if you check in the comments section below, I'll have a download link for this particular image if you'd like to follow along. When you save this out, you're going to be placing it into your project folder. So if you don't know where that is, go over to your Solution Explorer, right-click on your solution, open folder in File Explorer. That will open this up. Go into your project directory, and you'll notice I already have several images placed inside of here. Here, of course, I've placed my test pattern, and now I can refer to that inside of code very easily. Let's create our new function, minimize this one, void example2. So let's load in that object first. Let's do mat input is going to be equal to IamRead, and then that's going to be the name of our image, which was testpatterns.png. So let's paste that in there. Next up is how we're going to read this in, and I'm going to say that this is a grayscale image, so IamRead grayscale. Now let's go ahead and create a structure element without using the getStructureElement function. Instead, let's use a standard mat object that will modify using the .at method. So let's do mat structure element cross is going to be equal to mat : zeros. The size will be 3 by 3. And its type is going to be CV_8U. 1 channel, size 8 bits, that are unsigned. Now let's modify this manually. So we can do structure element cross .at. And of course, now I need to specify the size, and that's going to be uint 8_t. Once again, we get this uint 8_t from the ctypes file. And now we specify the row and column we want to mess with. And I'm going to say that let's do the very centermost element is going to be equal to 255. So what does this look like? It's going to be a completely black 3 by 3 image except for the very center pixel, which is going to be a value of 1. So this is actually going to be a very trivial erosion that we're about to perform, because anywhere where the foreground matches the foreground of this image, which is going to be every location, we should end up with the exact same image back out. So now let's perform our erosion. So let's create a mat eroded matrix. And now let's do erode, and we will do our input. We will now do our eroded output, and then we will use our structure element cross. Now let's create our named window, and let's say original, and then we will do our input, and we will do a window underscore free ratio, and then we'll do our named window, and then we will do our kernel. We'll do window underscore free ratio. And finally, let's do another named window. And that one will be our erosion. We'll do window free ratio again. And now let's do our IamShows. IamShow times 3. Let's grab this, 2, 3, and we'll do original, kernel, and erosion. And let's specify our input, our structure cross element kernel, and finally the output, which is eroded. And we'll do a wait key 0. Let's go ahead and grab our method, paste it here so it gets called, and hit run. All right, so let's take a look really quick. So here's our original image, and here's our kernel. Like I had mentioned, this is going to be a trivial case. The reason for that is because we have made a structure element which is going to always agree with wherever our foreground is. We move the structure element to each element in the foreground, and we check to see if those foreground elements match. They should always match because this is the center, this is going to be the location. They're the exact same thing. Therefore, it passes and we get the exact same image back out. So let's go ahead and create a different kind of structure element. Why don't we do something a little bit different? Why don't we do something that highlights the horizontal elements? So what I mean by that is we're going to create a structure element that looks like this, 0, 0, 0, 1, 1, 1, 0, 0, 0. To do that, we're going to take our @ method and we are going to turn on these pixels to the left and to the right. So it's going to be row 1, column 0, row 1, column 2. Now let's go ahead and hit run. And here is our horizontal kernel now. And that horizontal kernel is going to be looking for areas that match in the horizontal shape. So what we can notice here is that if we take a look at areas such as the checkerboard, as this kernel moves over this original image, only areas that have this horizontal strip are going to stick around. And those areas with a horizontal strip are going to be the vertical components of this checker, each of these blocks. So you can see that that strip now persists for each one. Anywhere that strip does not exist, which are to the sides of this, it disappears. Same thing with the other elements as well. They all appear to be getting thinner while preserving the overall height of each of these individual objects. We can do the exact same thing again if we wanted to, or what might be more interesting is if instead of using a kernel of size 3 by 3, what if we used a much larger kernel? Now, to use larger kernels, it's going to be much easier for us, instead of directly manually changing these pixel locations, to just using one of these structure elements that gets created for us naturally. So let's go ahead over here, and instead of doing it this way, why don't we go ahead and use our getStructureElement function. Let's do getStructureElement, and in this time, let's do morph underscore, and let's use an ellipse as our kernel. Let's say its size is going to be a little bit larger. We'll do 5 by 5 this time. And that's all we need. And so that we can actually see what we're doing, I'm going to multiply this by 255 so that our output is actually going to be between the values of 0 and 255. So here's our kernel you can see right here, and it's got a little bit of a dent at the top and the bottom because of the ellipse that we've crafted. And then what you'll notice is because of the size of this is much larger, it becomes far more restrictive of what it's going to let through. We only get a portion of these different elements, only where that 5 by 5 is going to fit in there. In fact, the checkerboards have been completely removed. And if we wanted to make this even more exclusive, so that maybe we get rid of almost everything except for the most large elements, we can go in here and let's increase this to say 7 by 7 and hit run. Once again, omitting quite a bit now of the original image. And then finally, let's do something even larger. Let's see if we can take this up to 10 by 10 and how that is going to factor in. And then actually, in this case, we've gone up so high that none of the different components here are actually going to stick around for our erosion. So let's try 9 by 9 and see if we just get those largest elements. And there we go, 9 by 9 barely kept a little bit of this object right here. So as our final example, let's try to do something a little bit practical rather than these sort of thrown together examples that just show you how the functions work. In example 3 now, we are going to load in an image and try to subtract out different regions of it that we don't find interesting. In our case, we're going to get rid of the vertical and horizontal segments of a grid. So let's do void example 3. Now what you're going to want to do is search online, and that image is going to be of something along the lines of, let's see, I'll do grid numbers under images. And then what I ended up picking was a grid of numbers similar to this one right here, or this one, that's pretty much an already binary image, black and white, that I don't really have to edit or manipulate at all. If you use an image that's been scanned in or photographed, let's see if we can find one. Maybe something like this, for instance, where the values are changing quite a bit across the image, you're going to have a harder time extracting a mask. So for our simplified example, I really recommend you stick to something like this. There are other functions you can use in OpenCV, such as adaptive threshold, that will allow you to use images that have gradients of sort of light and darks across them, but we're not going to cover that in this lecture. So go ahead and grab your image and bring it into your project folder, as I showed before. So let's go over to Open Project and go to Project 1. And in this case, I have gridlines.png. So let's go ahead and copy that name, Control A, Control C. Let's go ahead and do an IamRead. So IamRead, and we'll do gridlines.png, and I'm going to do IamRead underscore grayscale. And let's set that equal to image is equal to that. Now, you'll notice that the original image actually has the grid lines in black in the background in white. I'm going to want to work with the exact opposite, so we're going to negate the image, that is reverse everything. So let's do image is going to be equal to not image. And if we go ahead and do a quick IM show, what you'll see is that by doing that operation, we flip-flop the colors around. Blacks become whites and whites become blacks. There we are. So heading on back, let's go ahead and move all this down. Now I'm going to try to make it so that we can create a kernel that only grabs the horizontal and vertical elements here of this grid, and will leave all of the numbers alone. How can we do that? Well, if we think about it, remember, the kernel is only going to grab those elements that it has 100% agreement in with the foreground elements. Therefore, if we choose elements in here that are larger than the numbers that we have, that encapsulate pretty much exactly what these grid lines are, will succeed. So for instance, if we were to create an element that is about this long, that is as long as one of these grid elements, we're always going to exclude the numbers because none of the numbers are that wide or that tall. So let's go ahead and do something like that. So we're going to create two different structure elements for this. We're going to do a horizontal structure element and a vertical structure element. It's going to actually take 2 passes for us to grab all this information and remove it from our images. So let's do a mat horizontal structure element is going to be equal to get structuring element, and we're going to do a morph rect, and let's do a size, and that size I'm going to base on the actual size that we expect this to be inside the image, because technically the image could be a variable different sizes. I don't want to have to manually try to put the pixels in, so we're going to use the actual number of columns in the image and the number of rows to kind of determine what exactly we should be using as a structure element. I'm going to use the image dot columns divided by, and for right now, let's just try something like 20. If this isn't big enough or it's too small, we'll come back and adjust this value as necessary. And then I'm going to say that it's only going to be height of 1. Now let's do a mat vertical structure element is going to be equal to another get structuring element, but we're going to flip things around now. Instead of it being the columns divided by 20, it's going to be the number of rows. And the height on this is only going to be of size 1. Now we're going to perform 2 erosion operations. Let's do a mat horizontal erode, and we'll do another mat object vertical erode. And let's do erode, and we're going to use the original image, and then we're going to output this first to horizontal erode, and then we're going to use the horizontal structure element for that erosion. Then we're going to do a second erode, image, the original image, vertical erode, and then we're going to do a vertical structure element for that erosion as well. So let's go ahead and see the output of these erosions and see if we're getting anything that makes sense. So let's go ahead and do an IM show, and the first one will be horizontal erosion, and we'll do H erode, and then we'll do a second one, which will be vertical erosion. And let's go ahead and hit run. And here are 2 different images. So what we'll notice is with the horizontal one, we were able to get only the horizontal lines with our value of 20, so that worked perfectly. However, you'll notice that with our value of 20 for the rows instead, we were able to grab parts of the different numbers, which we do not want. Therefore, we're going to increase our size a bit. So instead of it being divided by 20, we're going to make it a little bit larger. Let's try 15 and see if that's a little bit closer. Let's go ahead and hit run now. And very close now, we only have a very small bit of the elements actually still grabbing the numbers. So let's go ahead and move this to 10 now, and that should be perfect. And there we are. Now we've grabbed just the horizontal and vertical elements. So let's go ahead and now subtract these masks away from the original image so that we only have an image now with the numbers and none of the grid lines. So we'll do image is going to be equal to the original image minus the horizontal erosion minus the vertical erosion. And then we are going to visualize our final image. We'll do IM show, final, and then we'll do image. Let's go ahead and hit run. And here we are. So our horizontal and our vertical as we saw before. And of course, subtracting those masks from the original image give us this, where all we have left are the original numbers and we have none of the lines. So hopefully this was more of an interesting practical application of how you could use erosion to remove different elements by grabbing a mask and then cutting them out. And of course, if we wanted to, we could always invert this back to the way it was. So we'll put the not operator in and hit run again. And then that way we'll have the original image black and white, as you can see here. I hope you enjoyed this video. As you can see, erosion is a very powerful morphological operator. In subsequent videos, we'll be covering the other kinds of morphological operators. Of course, dilation will be coming up next, followed by some of the more interesting ones which actually combine both erosion and dilation to produce interesting effects. Thank you all for watching. I'll see you all next time. So long and goodbye.